And here, please welcome Jan Goetz. Jan Goetz is a quantum physicist and CEO and co-founder of IQM Quantum Computers, which is the leading European vendor of quantum computers based on superconducting technology. Together with an international team of quantum experts, they are developing co-designed quantum computers to tackle the hardest challenges of modern society. Welcome, Jan.
Hello, welcome. It's great to be here. And thanks, the organizers, for giving me the opportunity to present what we're doing and how we fit into the ecosystem. Let me share my screen for this. I hope this works. All right. So yes, the title of my presentation, actually, it's quite lengthy, enabling the next level of scientific exploration and industrial innovation with quantum accelerated HPC. But what it means, I think, is very well illustrated here in this picture, which is a rendering, and what you see here is a view maybe into a future supercomputing center. So all the black boxes that you see in the background, these are racks filled with classical computers. When we talk about quantum acceleration or quantum accelerators, actually it means that you have a quantum computer, which is, for example, placed inside the same building, and it's working hand in hand with the supercomputing or high-performance computing infrastructure that is available. And this is very much the kind of use of the technology that we also believe in IQM. It's this kind of hybrid way of using, and what we do, you see there as also our slogan, we build quantum computers. So what we bring into the equation actually is the quantum computer, the complete system. So if you wish, our product is the complete quantum computer, and the targeted users at the moment are the supercomputing centers. And since the technology is not yet there where it solves maybe commercial problems, we also think that the early use cases are very much about science, enabling science, maybe accelerating also science. And then I think also another concept that's super important is the education actually that you can do on these systems. And this is kind of a summary of the presentation that I will give you today, kind of how do we come to this conclusion, and what are our activities here in this direction. Just as a short reminder about the company itself. So IQM, we see ourselves very much as a European company. We started in Finland, but meanwhile we also have operations in Munich and in Madrid and Paris, actually, where I'm currently sitting in our Paris office. And we are building the quantum computer with, at the moment, around 160 people, really great experts from the field, focusing a lot on the processor technology as such. So our processors are based on superconducting technology, which is one of the more widely used technologies, and we are designing the processors in-house and then also fabricating the processors in-house. So we have access to a production line, but also ramping up our own production line actually, and then we build the complete system around it. So we see ourselves there as kind of a systems integrator, and which brings in the kind of key component, which is the processor, but then we also, of course, use a lot of third-party components and assemble a whole system. And this is then also the offering that we have. So we offer, for example, to these supercomputing centers to get a complete system from us. And we have two such cases, one in Finland and one in Munich. I will talk a little bit about where you can use these systems. And the idea is very much to integrate them into HPC centers. So this is kind of what we're developing towards. And another work stream that we have is that we say, okay, on the processor side, actually, it makes a lot of sense to design the processors for given algorithms to really get the best out of it from a hardware perspective. So this is very much kind of what we do in a nutshell. And to motivate a little bit also the title of the talk, I was reusing here a slide that I use usually to motivate the topic of quantum computing in general. And I guess here in the audience, the arguments, I guess, are more or less clear that quantum computing offers this kind of possibility to solve certain problems. Of course, we have to be careful here. It's not all problems that we have, but a certain class of problems with a quite significant speed up. And the speed up can actually be so big that it can give us answers to questions which otherwise we would never probably get or even ask. And there are some fundamental limits to it, but also then the pure computing time. And the interesting thing is, if you look at actually the potential use cases for quantum computers, which you see there on the right-hand side, you realize that actually quite many are somewhat related to science or coming from science or kind of very heavy R&D. So the majority of the use cases actually has either a scientific value or then an R&D value. And this is kind of why we think that now in these early days of quantum computing, it's really about tackling those problems which maybe come from quantum, for example, simulations in fundamental quantum physics or so. And then from there on, it will be a stepwise development towards more and more commercial use cases. So we really think that this kind of scientific computing is the kind of the link between the HPC, the high performance computing, and quantum. And I was using here a slide actually from our friends at HQS Quantum Simulations, which shows how in the US the supercomputing time is distributed. And there actually you see that quite a lot of the computing time on high performance computers actually goes into scientific computing, very fundamental questions of physics and even quantum physics. And there are just two examples which I think nicely show how you can use a quantum computer, and this probably goes back to Feynman's original idea, to emulate or solve certain problems from quantum physics. So this is why kind of we think that quantum computers, they will enable the scientific computing, but then of course on the long run also more and more the commercial use cases. And based on this assumption, in IQM, we have a strategy which is kind of separated in three phases, and we call them foundation phase, advantage, and disruption. And at the moment, we are in this foundation phase, which is characterized by the fact that the machines that we have, and I think also that others have, they're not yet powerful enough to solve commercial problems. But it doesn't mean that they don't have any value, but the value is exactly what I've been just describing. So you can do excellent science with these systems. So if you look at the number of publications, for example, that come out of the existing quantum computers that are available globally, there was really a ramp up in the numbers. But then also, of course, there's a lot of value in really making these systems accessible all the way down to the hardware level. This is what we believe in, that there's a lot of benefit to the community, to the ecosystem, if people get educated and trained on the actual systems, in comparison to only using it through the cloud for algorithmic purposes, but really offer this deep know-how. And we see this really as kind of building the ecosystem, creating the market, thinking about also then that we have all the companies that help with the supply chain. And this is what we are currently doing. And we think that one of the best places to do this actually is in the HPC centers and combining here two worlds, quantum and HPC. And then if we develop the technology further, of course, at some point there will be what people in the field call quantum advantage. And here we think it's about this kind of, they are very specialized processors for certain algorithms. And then at a later stage, we will enter this phase of general purpose quantum computing, which we call here disruption phase. But now this kind of HPC integration and the scientific computing is very much linked to the foundation phase. And in a sense, it should build the foundation for the commercial advantage. And only if we show that it actually works for these fundamental problems, I think then we are also ready to bring it to the commercial side. And this is what we are doing from a business perspective. And the first place where we did this was in Finland with the research center VTT. There we have delivered actually already a 5-qubit system, which is now operational on their premise. And it gets now an upgrade to a 20-qubit and then 50 qubit. So the idea here is really together with these research centers or also the HPC centers to go the path towards quantum advantage together and kind of also go through the learning curve together. And the second project, which we are very proud of, is in Germany, in Munich, a project funded by the BMBF, where we are bringing a quantum computer into an HPC environment. So in VTT, it's still very much a standalone system, and the uniqueness of the Munich project is that really we place the quantum computer inside the HPC center, and there's a lot of learning again then on both sides, on the HPC side and on our side, on how to do these things together. And of course, we think that these are not the last ones. And of course, quantum is at the moment seeing this kind of hype or very strong interest. And there are many national quantum programs out there. And most of them actually also have as one of the goals to get quantum computers into the supercomputing center. So we see actually there a lot of potential in developing this business model further. And if you just look at the, let's say, bare numbers in a bottom-up approach, look at the HPC market. For example, in Europe, we have something called the Euro HPC program. And there in 2021, you had around 70 HPC centers, which were kind of actively in purchasing hardware, not all quantum, but hardware in general. But we actually made a market study together with Atos and IDC, which said that by 2023, 76% of the HPC centers will use quantum. In the beginning, mainly still with remote access, but actually there's another number in the report is that by 2026, 71% will actually use on-premises systems. So this is kind of the baseline, and we see this very much as the foundation and the enabling factor then for the quantum advantage, which brings us access to all the different use cases. And also there, actually, we see that supercomputing has a big part of it. So we really think that now is the right time to work together with the supercomputing centers, which of course it's a very established field, and they are working in all the pressing and very important questions like climate change, simulations on weather forecasting, drug discovery, simulations on chemistry. So all these very important topics that needs to be solved, and kind of how can quantum help them is of course in providing solutions that they can use to scale the computing power. So the supercomputing centers, they have this constant innovation pressure to create more and more computing power and make it available to their users. And quantum is one of the technologies that might help. Of course, there are a few other novel computing concepts as well out there. So this is really the idea, and of course it's not going to happen overnight, but we think about how to do this in a kind of roadmap point of view. So we now start working, and it's really about discussing how much space do you need, how much cooling water, what's the level of vibration. All of these technical details need to be figured out. But then, of course, once we know how to put the quantum computers there, it's also really about how to you then handle the jobs, so the actually computations, and how do you manage this, that the algorithms are kind of executed so that in a hybrid way, part of it is being done on the quantum computer and part of it on the classical computer. So it's really a synergy of two systems. It's not so that quantum computer will replace, I think, the HPC market, but they really work hand in hand together. And where are we at the moment? Of course, there are different approaches, and I think they should be acknowledged because they have different pros and cons. And a lot of people, of course, are interested in using quantum computers through cloud or remote access, because, of course, not everyone wants to have or even has the resources to put a quantum computer into their basement. And this is also very important, that we have all of these cloud activities where people get educated on the algorithmic level and know how to run algorithms. But what we kind of bring in here is really the addition of kind of getting ready at the hardware level as well. And of course, this also has some benefits, for example, in security aspects and performance reasons as well. One of the things that is currently happening, for example, in Finland, I mentioned we have delivered there the 5-qubit system. You see it on the picture on the right. And Finland also has or is building currently a big supercomputing center, Lumi, in the north of Finland, Kajaani. And here we are connecting the two systems, and this is happening as we speak. So this is kind of a remote connection between a supercomputing center and a quantum computer. But we see really a lot of potential then also by bringing the quantum computer physically there. And this is what we are working towards at IQM, is really making a product offer here where we can offer the HPC centers an integrated system, which then gets integrated either at the software level. Probably in the beginning, it's about kind of how do you connect it from a software architecture point of view, but maybe in the future also on a hardware level, that you have really, let's say, real-time, low latency feedback between the two systems. And for example, in these variational problems, that this might be a topic. But also, if you think about error correction, actually, there's a lot of information that needs to be passed back and forth between the classical computer and the quantum computer. And this is what we are working on. It's still very much R&D work. So we are thinking about the technical limitations on the hardware side, on the software side. What is really the latency that we need? What is the bandwidth? And we are working there very closely with a few partners in Munich, in Finland, but then also on an industry scale, for example, with Atos. So I brought a few examples what we are doing, and the first one actually is a BMBF funded project, which is more on the R&D side still. It is about exploring a new or a different quantum computing paradigm called digital analog quantum computing. So this is why we call it DAQ here, and this is done with a few partners. LRZ is one of them, but then also Jülich, another research institution or HPC center is involved, and Infineon. And there we will actually build an experimental platform in Munich. We will have some of our processors in Jülich, and in this way try to connect the different worlds of high performance and quantum computing on a more experimental side. But then the other project, which is much more focused and much more targeted towards this HPC integration, is the delivery project that we have with LRZ. And there are also two other partners, Atos and HQS Quantum Simulations involved. And together there we are really aiming to build a fully integrated 20-qubit quantum accelerator in Munich, which kind of covers the full stack also on the scientific computing side. So actually it contains a scientific computing platform that is being developed by AQS to address some of the interesting problems in chemistry. And then there will also be a simulation backend from Atos, this so-called Atos QLM. And in this way, the user in the end will be able to kind of test their algorithms, their scientific algorithms, for example, maybe first simulate them on an Atos QLM and then switch to the real hardware from us. So this is kind of the idea of the workflow that we are doing there. And of course, this should not be the end, but we are really thinking here about developing, let's say, a roadmap that will carry us in the future also. And we think that quantum, of course, is there to stay, and it's there to stay within the HPC environment. So now we are kind of just at the beginning where we maybe have the first devices operational in the HPC environments, and we will see what kind of challenges this brings and what kind of opportunities this has as well. We are, for example, integrating now from a software perspective, all this kind of middleware. So there's a strong learning curve also there, kind of how do you, for example, use concepts from HPC, from the HPC software architecture then and apply it to the quantum computing stack. And this is what we're doing. And we're doing this, of course, in a constant exchange with the end users. And we are very active there. We are, for example, at the moment also drafting a few papers or white papers with some other players from the high performance computing field. We are trying to kind of get in contact also with different communities, for example, from the climate sector, where it's about modeling of the global climate development. So we try to explore where high performance computing and quantum computing can really benefit from working hand in hand, and then maybe in the future also build these application specific processors, these QASICs, for exactly those problems where we think HPC and quantum can go hand in hand. And of course, we do this with the motivation that there is a business behind it. And then in business, what you need at some point, if you want to scale it, at least on industrial scale, is that you need to agree on standards. And I think when you talk about standards, it's about interfaces a lot. And the quantum HPC integration, actually, it by definition, it creates an interface between the systems. And for example, I think this is a very important topic that also there, then globally, we agree on some industry standards, which currently are not there yet, but are being developed in the background. And this is also something that we are actively contributing to. All right, so this brings me to the end of my presentation. And I can take questions if this is planned.
Thank you very much, Jan, for an interesting presentation. Unfortunately, we don't have time for questions now when you have to move to the next agenda point. However, we will meet Jan again tonight at 6 o'clock during our fireside chat. And there we will learn more about IQM technology and integration of quantum computing and high-performance computing. And we will also be joined by a colleague from Ethos. So visit us at 6 o'clock tonight during the fireside chat, and then you can also ask your questions to Jan Goetz.